Welcome to Unit 5 on sampling distributions. In this video, we're going to focus on topic 5.4, bias and unbiased estimates. So when I think about sampling, looking for a true population parameter by taking a sample from that population, I think about shooting arrows at a bullseye, right? And the idea is that we're aiming for the bullseye. So you could think of like the bullseye as the truth. So we're aiming maybe for the true mean, mu. And if you think about it, a couple different things can happen when you're aiming for the truth. One is that all of your shots, all of your samples are very widespread, right? You have high variability, which means that, you're getting samples, but a lot of them are pretty far away from the truth. Now, this is typically going to happen when you have small sample sizes. Small sample sizes, like if you have a sample of 2 or 5, I don't want to say they're unreliable, but they're just going to create a lot of variability. And we know that bigger samples will produce less variability on average, which will get those, arrows closer to the target. So once again, here's an example of that. If we're aiming for the true mean, and all of our samples are, some of them are really, really close to that true value, well, that's going to have very low variability. And obviously, that's what we're after. We're after for low variability. We want our samples to be really close to the truth. And that's going to happen with large sample sizes. And that actually boils down to the law of large numbers. If you have bigger numbers in your sample, if your sample size is bigger, then you're more accurately going to reflect the truth. Smaller samples, it's not that they're bad, they're just going to create more variability. Now, something else that can happen is this. If you have a bias estimate, so you have a bunch of samples that are all coming back somewhere over here. So you actually have low variability. All of those arrows are really close to each other. In this case, all of those samples are very close to each other, but they're way far off from the truth. This is going to create a bias, meaning something is happening. Like your samples are not, they're accurate in of themselves, but they're not accurate to measuring the truth that you're aiming for. Now, this is going to typically happen because your samples aren't random. Maybe you self-selected, maybe you use volunteers, or maybe you thought you were selecting your sample from the overall population, but you're actually not doing that. So again, we have low variability, but our samples just aren't even close to what the truth is. And that's what creates this bias. Or if you really want a terrible result, this would be terrible, right? This is going to have high variability, and it's going to be biased. That is the absolute worst, right? So, what we're aiming for is this. We're aiming for no bias, which means our estimates are really close to the truth, and low variability. Now, this one right here would be like second place. There's high variability, but at least, we're getting close to the truth. At least we're surrounding the truth. And again, these ones down here are bad. Even if you have low variability, if you're biased, none of your samples are going to even be near the truth. So that'd be terrible as well. And then obviously having high variability and being biased is really going to be equally bad. So that's just kind of how I look at, sampling, and we're trying to find the truth and thinking about how your sample statistics are going to vary around that truth. So let's talk about this a little bit more specifically for statistics, not thinking about shooting arrows at a dart board. So first, we got to understand what it's called a point estimate. A point estimate is a statistic from a sample that is being used as an estimate of a population parameter. So, we're looking in the majority of cases in this classroom, we're looking at an X bar that is a sample statistic, that is a mean from a sample that we're hoping is going to be an estimate of the truth. Or we're looking at a p hat that is a sample proportion, a proportion found from a sample that we are really hoping is going to help us estimate a true population proportion. These numbers are called point estimates. Okay, they're single values from one sample that we're hoping will point us to the truth. Here's a couple of examples. Maybe a sample, we use N as sample size. A sample of 125 adults shows 73% brush their teeth daily. So this being a p-hat, a proportion from a sample, that's going to be my point estimate. I'm hoping that that one single value from one single sample, boy, I'm hoping that it's close to the truth. Here's another example. 55 bullfrogs have a mean weight of 15.2 ounces. That is an X bar. And again, that is an estimate from my one sample, and I'm really hoping that it points me to the truth, right? Point estimate. Here's another sample, 120 houses, and the median price of those 120 houses is $205,900. This is, we don't really have a symbol for the median of a sample, so we just put median. But again, this is a statistic being used as an estimate for the truth. So these are point estimates. We've already learned about these things. We're just giving them a different name. But I will say that we don't really typically deal with medians too much in this class. We typically deal with means, X bar, and p-hats, proportions. All right, now, an unbiased point estimate. To figure this out, right, if you want to be unbiased, you got to think of it this way. When estimating a population parameter, an estimator is unbiased if, on average, the value of that estimator is equal to the population parameter. Now, I'm not talking about one sample statistic being equal to the parameter. I'm talking about the average of many statistics. So the idea here is we're talking about on average, right? A mean. So we're not talking about a single mean being equal to the truth. We're talking about the mean of a bunch of means being equal to the truth. Or the same thing with proportions, right? I'm not talking about one single proportion from a sample being equal to the truth. I'm talking about the mean of a bunch of p-hats being equal to the truth. And of course, that directly relates to sampling distributions. Because remember, a sampling distribution is showing you a whole bunch of X bars, and the mean of all those X bars should be in the middle. And what I'm telling you is that that middle is the truth. That's a sign that you're unbiased. Now, the opposite of this would be if your estimator, on average, is far from the truth. Well, then obviously that's going to be when you create bias. So let's kind of understand this through a picture, for example. Here is a number line, and right here is the true mean. If you start to take samples and you find the mean of your sample, and they consistently stack up near that truth. Now, it does follow a normal model, so some samples are naturally going to be on the low end, a little bit lower. Some samples might naturally be a little bit higher, but if they consistently, on average, fall near the truth, then that means you're unbiased. On average, your X bars are all near the truth. That's going to be unbiased. But if your truth is over here and your samples stack up over here somewhere, and some are going to be higher, some are going to be lower, but they start stacking up, and again, creating a normal model, they start stacking up somewhere far from the truth, well, then that means you're biased. Something about your samples is biased. Like maybe it was not random. Maybe your population was all adults, but you only were looking at samples of females. So no wonder you were lower or high. I don't know. But the point is that when you on average have samples that stack up near the truth, you're unbiased. And when you have samples that stack up away from the truth, that's when you're going to be biased. So let's look at this a little bit more specifically with an example. So here is the sampling distribution for the mean weight of a sample of 55 bullfrogs. So this is a sampling distribution looking at the mean, and we used sample size 55 bullfrogs. Now, remember that we learned, this video does connect to the previous video, we learned the sampling distribution shows every single possible sample of size 55. Well, that's a lot. I mean, there's lots of bullfrogs out there, and there's got to be billions of samples of size 55. So that's why, I can't actually do it, but we could use a model. And because of the central limit theorem, we know that that model is going to be normal. So if we were to envision this sampling distribution that represents the mean of all possible samples of 55, we notice that it starts to stack up around 14.8. And yeah, there's going to be some deviation, right? There's a little bit of deviation down, 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 a little bit of deviation up, up, up. But the mean of all these means that are in this picture, right? Well, that's going to be 14.8. And as long as we are unbiased, that mean of 14.8 should also reflect the true mean of all bullfrogs in the entire world. So this is how sampling distributions really, 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 really help us. If they're a good sampling distribution based on truly random samples from the population, then those sample means that are shown in a sampling distribution should start to stack up at the true mean. And yes, maybe your one sample comes back a little low, or maybe one sample comes back a little high. But remember, unbiased does not tie your one sample to the truth. Unbiased is tying the center, the mean of all sample means to the truth. And that's what a sampling distribution shows us if it's unbiased. All right, so here's a fact. When estimating a population parameter, an estimator, a single estimator, exhibits variability that can be modeled using probability. What am I saying here? Through a sampling distribution that follows a normal distribution, we can find our sample's point estimate and calculate the probability of such a sample occurring. So what we're trying to say here is that what we just got done explaining was that when you look at the mean of all your samples, it's going to be the truth. That's unbiased. But any one single sample mean is going to exhibit some variability, right? It's going to be a little higher, going to be a little lower, what have you. But we could actually calculate the probability of any one single sample, or higher or lower. Remember, the normal model can only do intervals, above or below, using the normal model. So let's put this to use. Okay, back to our sampling distribution for bullfrogs. Our one sample, one particular sample, came back at 15.2. This is just one sample. 15.2 is somewhere around here. Now, I want to figure out, since this is the normal model, what's the probability of my sample occurring or more extreme. Please remember, with the normal model, you cannot calculate individual probability. So at no point can I say, hey, what's the probability of a sample being 15.2? That's impossible. But what I can do is I can find the probability of my sample being greater than or equal to 15.2. Now, how do I do that? Well, I hope everybody knows, to utilize normal CDF on your calculator, you do need a z-score. So I'm going to take my 15.2, and I have to subtract the mean. The mean of this model is pretty clearly the center at 14.8. Now, I need to divide that by the standard deviation. So how the heck can I find a standard deviation? Well, remember, one standard deviation is how much you go up or how much you go down. And we do that 3 times on each side. So one standard deviation could simply be found by taking that 15.01 and subtracting the 14.8. So 0.21 must be my standard deviation, 0.21 must be my standard deviation. Whether I go up or down, it's the same. And if I go up another 0.21, that's where the 15.32 comes from. Go up another, that's 15.53 comes from. So my standard deviation is 0.21. So guys, all I'm doing is finding a z-score by taking the sample that I got, 15.2, subtracted by the average of them all, divided by the standard deviation of them all. So 15.2 minus 14.8 divided by 0.21 is a z-score of 1.9048. So now I want to find the probability of a z-score being greater than or equal to 1.9048. And to utilize that, or to find that, I'm going to have to use normal CDF. I'm going to start at that z-score, and I'm going to go to infinity with the standard deviation, or the mean of 0, standard deviation of 1. And this is how I'm going to do it on the calculator. We've done this before in plenty of videos. This is actually why we spent that whole topic on revisiting the normal model, so that way you guys remember all this. And we get 0.0284. So remember, a sampling distribution shows me what all possible x bars look like of size 55. My sample came back at 15.2. I want to know how likely my sample is. Why do I want to know this? Because samples vary, right? My sample came back a little higher. But I want to specifically find the probability of my sample occurring or more extreme. Please remember, we can only do higher than values or lower than values, or we can even do in between two values, but we cannot do exact values. So 2.84% is the probability the sample comes back 15.2 or more extreme. In this case, that would be or higher. This actually has a name. This type of probability we call a p-value. This is a very, very, very specific probability, which is why we're giving it this special name, p-value. We don't call any probability a p-value, only a probability of a sample statistic occurring or more extreme, given that the population parameter is in the center of the distribution. Why do I have to say that last part? Well, my goodness. If the population parameter is not in the center of the distribution, then I am biased. And I wouldn't recommend calculating any probabilities if your data is biased. So I need to give that extra given there because I need to confirm that this is an unbiased model. And remember, what does unbiased mean? It means that the average of all my samples, not one, the average of all samples is equal to the truth. So again, this is a very, very specific name. So we have done lots of probability questions before. Don't start calling any probability a p-value. A p-value is very specifically the probability of a statistic occurring or more extreme. Now that could be higher or lower. So if we go back to my sample, 15.2 was already higher. So I looked even higher. If my sample statistic was below the mean, then I would look even lower to find the extreme. Now, this phrase p-value only applies to sampling distributions. So all the other probabilities that we've done before that deal with populations or deal with individual things, do not use that term p-value for, please. All right, so let's do another example, because the more examples you see, the more familiar you will get with this. All right, what proportion of newborn babies have torticollis? Torticollis is a twisting of a baby's neck. Not really a major issue, but something that obviously parents should be concerned with. So we conducted a sample of 75 babies, and of those babies, 19 had torticollis. This is a p-hat. This is the proportion of a sample. 19 out of 75 is 25.3%, 0.253. So 25.3% would be considered a point estimate for our proportion of babies with torticollis. But what does it tell us? Honestly, just that number all by itself tells me nothing. Is that a high number? Is that a low number? Is 19 out of 75 babies a lot of babies, or is that a little babies? I don't really know. In order to understand how our one sample fits in, we need to contemplate what all possible sample proportions of 75 look like. And this is, of course, a sampling distribution. and this is what I've tried to connect to you in the last couple of videos, is that looking at one sample in of itself honestly tells us nothing. We need to think of many samples. Then we could see where our one sample fits in. So typically, to make a sampling distribution, because there's so many samples out there, we have a computer generated for us. So I went ahead and had a computer generate what would happen if we looked at many samples of 75 babies. And for every sample, we look at the proportion that have torticollis. And this is what I came up with. So as long as it is a unbiased sample, sampling distribution, the mean of all my p-hats, the center of all the p-hats, some are low, but the center is 0.14. Now, remember what that means. That means that the true proportion of babies with torticollis is 14%, as long as I am unbiased, which I'm hoping I am. Unbiased means I'm selecting my samples randomly from all babies, not selecting anything at random. Like if I'm just going to pick my favorite babies or the cute babies or the ugly babies, or if I'm only going to pick female babies, well, then obviously you're going to be biased. So I'm assuming that this to be true. And this is really important. This is I'm kind of talking normal about this, but this is super exciting stuff, that the center of a sampling distribution that is unbiased is the truth. So now the question is, where does my sample fit in? Well, to understand where my sample fits in, I have to understand the shape, the center, and the spread. Well, we already talked about the center. The mean of all the p-hats is the center, 0.14. What about the standard deviation? Well, I kind of made it easy on this problem for you. But if we go up 1, up 2, up 3, that's the standard deviations. So it looks like a standard deviation is 0.04. Up 0.04, up 0.04, up 0.04, down, down, down. And of course, the shape is normal. Now, this is awesome. Now, what this allows me to do is to see where my sample fits in. Let's recall that my sample was 0.253. I now am seeing that that sample seems to be pretty unusually high. But what is the p-value? Remember, the p-value is the probability of my sample occurring or more extreme, which in this case would be even higher. So I need to find the probability of a sample coming back equal to or higher than 0.253. To do that, I need a z-score. So I got to find the z-score of my sample, 0.253 minus 0.14 divided by 0.04, standard deviation. So I'm going to go to my calculator, 0.253 minus 0.14 divided by 0.04 is a z-score of 2.825. I take that back, 2.825. Yeah. So now I need to find the probability of a z-score being greater than or equal to 2.825. And to do that, I'm going to use normal CDF on my calculator. I'm going to go from 2.825 to infinity, mean of 1, standard deviation, mean of 0, standard deviation of 1. Go ahead and do that, 2.825. And I get a probability of 0.0024. And I'm not surprised that it's so low, because looking at the picture, I could see how unbelievably high this sample would be. So what does all this mean? Well, now I could go back to my sample and be like, whoa, what's going on with my sample? If my sample of 75 babies truly was random, something is going on. That sample has an extremely high amount of babies with torticollis. So maybe that sample was selected from a particular city. And maybe I should go and talk to the people in that city, like, hey, you're doing something wrong. Your babies have this condition where their necks are being twisted. What's going on in this city? The point is that when something this significant, this extreme happens, there's got to be a reason. And that's something that would be worth me finding out. So kind of a recap for this video is, first off, we talk about we want to be unbiased. And unbiased means that the center of your sampling distribution, the mean of all of your statistics, should be equal to the truth. And that's really powerful information. I'm kind of downplaying that with my emotion right now. I should be more excited, but that's really important information. And that allows me to understand where my samples fit in, right? Because once you understand a sampling distribution, trying to show you the, all possible statistics of your data, then you could start to see if your sample is weird or not. And then that can tell you something about your sample. So, if we go back to this problem, right? If my sample of 75 babies came from a hospital in Youngstown, Ohio. Now, the data clearly shows here that that sample has a very high amount of babies with torticollis. So that should be alarming to me, right? Maybe the doctors are doing something poor at that hospital. Maybe when they're taking the babies out, they're twisting their necks, and those doctors should be fired, or there should be an investigation into what's going on at this hospital. Maybe the nurses are laying the babies down in a weird way. It all goes back to sampling distribution. The picture shows me that 14% of babies should have torticollis. That's normal. That's just what happens in life. Not every baby's perfect. 14% have this condition. What are you going to do? But when we have a sample that's extremely high or extremely low, we need to figure out what's wrong. So let me just talk about the extreme low for one more time. Let's just say our sample came back way down here. Well, if that was the case, maybe the doctors at that hospital should be rewarded. They're doing something right that's preventing torticollis. So don't always think about the negative, think about the positive, right? And then we talked about in this video the definition of a p-value. We've been finding probability for a long time now. But a p-value is a very specific probability. It's the probability of a sample statistic occurring or more extreme. Higher if it's already higher, or lower if it's already lower. So hopefully this is it's still a longer video, but hopefully it's one that kind of starts to connect probability to sampling distributions, and it really starts to tie everything we've learned in together. Because the big theme of this unit is that one sample by itself honestly tells you nothing. It's not until you compare that one sample to all other samples just like it that you really get the feel for what your sample is, normal or weird. And that's important data moving forward. All right, guys, see you in the next video.